we start our live stream with recitation of Ummul Kitab Al-Fatihah. Okay, welcome everyone to the live stream. So this is live stream about the identification of unknown using TLC and MP melting point in combination. So during this live stream, I will ask you a few questions. So whoever can answer that will get a bonus mark. One question will you get, if you answer that, you will get one bonus mark. The maximum mark that you can get is 3. So meaning that if you can answer 4, your mark still 3. During the live stream also, you can ask me any question related to the live stream itself, the experiment that I conduct. So feel free to interject me if you want to ask the question. This live stream might take around 1.5 hours. I try to do it, finish it early, but we don't know. We will see, because during live, you don't know what will happen. But I try my best to stay on time lah. What else? So without further ado, we can start now lah. Okay, if you see in front of you, this is our plan for today: identification of unknown by melting point and thin layer chromatography. If you look here, there are 4 parts for this experiment live stream today. 5 parts. You have one here: preparation of unknown, preparation of TLC plate, spotting, and then preparation of developing solvent, and then you develop the TLC plate and visualization. So let's focus first here. The first one, preparing the unknown for melting point and TLC. The task for this live stream is like this: you will be asked to detect, to identify 2 unknown out of 12. 2 unknown out of 12 known sample. 2 unknown, and that 2 unknown coming from the 12 sample. So that's the idea. Previously, you are doing this melting point and you detect which one is which by using mixture melting point. I will not go detail on melting point because we have another live stream on that. You can check it that. But now, what we'll do today is that we check the melting point. Instead of using mixture melting point, now we are using the TLC method in order to identify what is our unknown. So before that, let's go and learn a little bit about the idea of the TLC itself. So let me change the view. So can you see the 3 camera now? Can you see this?
Yes.
Main view, side view, me. Okay, so let's put somewhere else. Okay, first, as usual, I need to wear the glove. So the first question: what is chromatography? Anyone? Question 1. Anyone? Say your name and answer.
Nisa.
Nisa. Okay, Nisa. Okay, what is chromatography?
Chromatography is a separation technique.
Separation technique. How people do it?
A mixture of compounds is resolved by distributing the components of the mixture.
Okay, so Nisa said that it's separating process that can be used to separate the different constituent in certain material lah. For example, let's say now I have this, say this pen, this green pen. I hope you can see. Okay, this green pen. Okay, so this pen is basically water based, meaning that water can dissolve whatever ink from this pen. When it dissolves, meaning that the water have the capability to push or to kick this pigment. If this green pigment is made up from different pigment, for example, let's say color A, color B, make this green, then you can separate that color using the TLC. But you cannot just put this this green color, whatever green water-based pen inside the water because it will dissolve everything. So you need something to hold this color. So that's why we need support. You can use support using this, what we call this tissue paper. The idea is that you can put a dot on this tissue paper like this, and then let the water kick this. Can you see, or is it too far? So let me make it down first. Okay. Okay. So for example, let's say I put the dot here. If I have water running from here, this pigment, if it made from two other color, it will kick this pigment up. Okay, it will kick the pigment up. So you need to put the water below this pigment in order to that happen. Because if you put the water and put on, this on top, not on top, meaning that you cover the pigment will be dissolved and you cannot separate. The separation happen because you have this support. You put the water and the water will run through the capillary reaction, and then while it's go here, it will kick this pigment to its constituent lah. So for example, let's say I have prepared this now here. Okay, you cannot see, I put here. Okay, so let me zoom a little bit because maybe it's quite far. So let me zoom a little bit. Where is zoom? Copy the video. Okay, wait. Okay, I need to zoom this first so that you can see clearly. Wait for a minute. Okay, so I will zoom this thing. Okay, so now I have this support, this what we call the tissue paper, and then I will put a dot. I will write the ink, this water-based ink on this paper. So just like that. And then now I have this, let's say this I put away. I have this beaker. Okay, I have this beaker, and then I want to fill the water. Why water? Because this is water-based. So I'm using water as a substance to kick this, what we call this pigment. So let's say I have water here. Okay, the question now. In chromatography, there are special name for this water or whatever solvent. What they are called? There are special name, special jargon for this whatever liquid here that I use to kick the solid or the pigment in this. What is the name for that? There are special term. Yes, name?
Maria.
Sorry?
Mariam.
Maria. Okay, so Mariam, what is the name?
Solvent.
Solvent, the name, I mean solvent, yes, but what is the term for that solvent? People use the key, the what we call the hint here is phase. What they call it? This solvent, yes, it's solvent, but they are special
mobile
term.
phase.
Yeah, mobile phase. Okay, so Mariam, that's correct. So that is mobile phase. Okay, another question, another person. So this pigment, we call what? If this is mobile phase, this is what? Anyone?
Stationary phase.
What's your name?
Nur Akila Husna.
Nur Akila Husna. Okay, so this is a stationary phase because it's it's immobile on this spot. So this, what we call this paper here, this thin tissue paper here, this we call it support. We don't call this stationary phase. Stationary phase is just a spot. The stationary phase is your compound that you want to separate. Okay, so now I put the what we call. So I can put here, and then I put. Make sure the water is not touching the what we call. Wait, yeah, the touch it. Okay. So if you see there, let me zoom there. No, I think you can see lah. Later on I bring in front. Okay, you can see. Okay, you can see now the water going up. Wait, let me zoom this thing. Okay. 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 Zoom. Okay, so this is not really lah. Okay, so you see the water is going up. Why the water going up? So the question, anyone? Because of why? Why the water going up? Question, give your name and answer.
Because the water is non-polar.
The water is non-polar. No, the water is polar actually. But what make the water going up? Because the water is bottom, but now you have what we call the tissue there and the water crawling up. Why that thing happen? What make that happen? Any idea? Iqbal lah.
Yes, sir.
Why? What make this what we call this water going up? Why not the water just stay at the bottom? Any idea? In order to get mark, you need to
Sir,
give
can I
answer.
try?
Yes, Mariam. Okay.
Yes. Is it because of the component of the paper?
Component of the paper. Yeah, but why? Why water going up? It's a component of the paper, but the reason.
Because the solvent has different polarity, and based on the intermolecular forces that's between the paper and the mixture, they react with each other, and then it makes the solvent go up.
Okay, that's one way lah to answer. But the easy answer is that because of capillary action. The name that the reason why the water can crawl up is because of capillary action. Inside this paper, okay, I put here. So we just left that here. So I will resume again, zoom out first. The reason why the water crawling up because inside this tissue paper, if you try to tear it, there are small fiber. Okay, this small fiber is basically like a straw. Okay, like a straw. Okay, I don't have straw here, but it's like a straw lah. You can imagine a straw, but it's very tiny straw. And when you have tiny straw, basically when you put on the water will be sucked up. So that's what we call capillary action. Okay, if the straw, you cannot do that using a straw. A normal straw, normally the diameter is too big. So when you put on the water surface, the water will not going up. But this so-called straw, the small straw, will capable to sort of like pull the water up due to the capillary action. So the key word here is capillary action. Okay, so I will let this thing, whatever happened here, stay there. So later on we will see, we will discuss about this. But for now, let's talk about what we will do today. The idea of today is that you have this 1, 2, 3, 6, and then 12. Okay, you have 12. Okay, you can see. Okay, you have 12 samples. 12 samples, so all the sample is like this lah. Okay, all the sample like this. All the sample is a known sample because on top of that, they are what we call, they are named. Okay, so this sample is basically in table 2.2 if I'm not mistaken. So to make it easy, I put here the what is the thing? So like this. Okay, so this. Wait, yeah, go there. Okay. So this, can you see? So let me zoom out for a while, this thing. Okay, can you see that? Okay. So basically, this 12 sample is this, all these things. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so they have 12 of that. Can you see that? Is it okay? Can you see?
Yes, sir.
Okay. So this in your table, I don't remember, but you can check in your lab manual. There are table, they show the sample, and also let me see what table is that. Yeah, this one. Can you see it? Table 2.2. Compound use STLC and MP unknowns. So this table I put here. So this table is basically they showing you the melting point for each compound. Okay. So rough melting point for each compound. So now the idea for this experiment is that I will give you these two unknown, X and Y. Your task is to basically find what is X, what is Y. The X and Y come from either two of these. So that's the idea. In order to find that, so we will find that X and Y using melting point and TLC combination lah. Okay, but before we do that, let's talk a little bit about the TLC itself. Okay, thin layer chromatography. If you see here, if you see on the side here, I'm using the tissue paper. But if you can see, the tissue paper is quite like not stiff lah. So it's very difficult to handle. That's one thing. It's very difficult to handle. And also the distribution of fiber inside this might be not, what we call, might not be homogeneous. So that's my effect lah. It can give you different result if you do different batch. So that's why when people do TLC, people normally use this. I put this away first. They use this thing. Okay. So this is, you can see, right? Let me zoom first. I cannot physically zoom. I need to use software to zoom it. So that's a little bit problem lah. Okay. So can you read this thing? Is it clear for you from your point?
Yes, sir.
What they call it? TLC silica gel, right?
Silica gel, yes.
Okay. So TLC silica gel is basically just a piece of aluminium like this, and then they put silica on top of it. Okay. So this is the example of that. Okay. So you can see this. So this I can take one. Take one. Okay, so there are many. Normally they sell in big square, but now the technician already cut it into small square that normally people use for TLC chromatography lah. So let's see this thin film. Okay, compare with this tissue paper. Now you have something that is more stiffer lah, so easy to handle. That's one thing. Second thing is that if you see, there are two sides of this. Okay, there are two sides. One side is shiny, one side is white. Is white lah. Okay, so this, the one that is white, is the active side. They put silica. Normally silica is something like this lah. This is not silica, but silica powder is more or less like this. It's white in color. They put silica on top of this. They sort of like immobilize the silica on top of this TLC plate. Previously, people don't have this. Previously, what they do is that they take the glass slide. I don't have a glass slide, but you can imagine, let's say this is a glass slide, and then they just spread the silica. They just put the silica on top of that, and then they fix the silica on top of the glass slide. But now, to make things easy, they just pre-make this silica TLC plate. If you, what we call, read this, it called TLC, thin layer chromatography. Silica, meaning that on top of it is a silica gel lah. 60, what is 60? I also don't know. Maybe the size, maybe the particle size, whatever. So 60, I don't know. This F254, you can see here, they are F254 here. Okay. So that means fluorescence at 254 nanometer. Okay. Inside this silica gel, they are gypsum. Gypsum. I think gypsum. How to aja? Gypsum. They are gypsum. Okay, they are gypsum inside the silica gel. So they are sort of like mix them together. The purpose of this gypsum is like a mineral. Gypsum is a mineral. For example, yeah, it's a mineral. So I can go here. Let's say I wait. Wait for a minute. I need to bring here first. Okay, I switch a little bit now. So gypsum, GYPSUM, enter. Why is board? I don't want board. I want gypsum only. Gypsum only, and then we go to image. Gypsum board again. Gypsum mineral. Mineral. You see gypsum mineral. So this is gypsum. Gypsum. Gypsum mineral fluorescence. Fluorescence. Okay, the gypsum have properties that it can fluoresce at certain wavelength. If you have a UV light and then you shine the UV light on gypsum, it gives you this greenish color thingy like that. Okay, so that is gypsum, gypsum. Okay, so that is what they bind the silica with. Okay, the reason for that, why they need fluorescence? Okay, the question now, why they need to bind gypsum to give fluorescence? Anyone? What is the reason they need to add gypsum? Why they need fluorescence at all? Anyone want to answer that? Try that. No? Okay, if you look here, it's okay. If you look here, it's easy to see the color. For example, here you can see I bring this thing. So now it's already separating to yellow and blue there. You can see it's separate yellow and blue. So the blue on the top, yellow at the bottom. This is easy. You can see it's separate because they have color. So that's easy for you to see whether it's separate or not. But normally when you do, when you try to check the compound like this, for example, compound like this, when you try to dissolve it, normally they are colorless. Most of the organic solvent is colorless. So because of that, they need to find a way to show a color, to induce a color for that compound. So that's why they put gypsum, they bind gypsum in this TLC plate in order to induce color later on for visualization. Imagine now you have this and then you dissolve it, you have like something that is colorless like this, and then you put on this and then it dry and then you cannot see anything. Okay. So because of that, they put gypsum so that later on, after you finish all the TLC, you can have the UV light put on top of it, and then the UV light will sort of like give color, give sort of like color fluorescence this TLC plate. So that's the reason why they put gypsum. So the F254 meaning that it used 254 nanometer wavelength. If you look at, wait, it's too messy here. I need to be careful. Okay, so this is example of UV light. This example of UV light. Let me make it. Where is the thing? Okay, let me zoom out first. Okay, this example of UV light that we will use later on. Okay, UV light. In the lab, you will see something called laminar flow. Laminar flow, then there are UV people work with bacteria inside the laminar flow. And normally that laminar flow, for example, this thing, let me set laminar cabinet. Laminar flow cabinet. Okay, let me check first. Okay, so typically, as you can see in front of you, this is typical laminar flow in the lab. And normally, they have the UV capability. The lamp here, you can change to UV lah. The reason for that, before people come and do their work inside the laminar flow, they want their place very sterile. So that's the reason they have UV. UV can kill, basically UV can kill the bacteria because they are more energetic than normal light. Okay, normal light, the wavelength is around 400 to 800. But if you see UV, if you see here, the UV here, 254. Okay, the smaller the wavelength, so this 254 is basically the wavelength of the UV light. So the smaller of the wavelength of any electromagnetic spectrum, the higher the energy they have. So the higher the energy that they have, meaning that they can penetrate to your cell and create havoc lah. So that's why if you see something like this, it can be very dangerous lah. So that's why when people open the laminar flow, then when they switch on the UV, they will go away. Okay, they let them the laminar flow to sterilize first, and then after for few minutes they close the UV, and then after that they start working lah. They open the normal light again. So this is example of UV light lah, handheld UV light. If you see here, can you see? You can see. There are two, what we call two wavelength, 254. Can you see? Is it clear?
Yes, sir.
Okay. You see 254, 365. Okay. So 365 is longer UV light. 254 is smaller long UV light. 365 UV light is typically used to check the counterfeit money lah. If you have money and if I shine it on top of that, you can see the fluorescence. But the UV light that they use, normally they call it black light, is this 365, the long wave. Being long wave, it have less energy than the short wave. So it's safer for people to use this to check whether you have the fake money or not. So when you go to the shop, the cashier, they check your money. They use this, the long wave UV light. The short wave UV light, the 254, is basically more energetic and can kill the bacteria, and also for that matter can not kill, but damage your skin. Okay, damage your skin and so on. So that's basically about the UV light. Later on we will see that again. Okay. So now what's next is, let's put it away and then let's see this first. Okay. So that's the idea of TLC, thin layer chromatography. It's thin. It's thin. You see, it's thin. And chromatography is the one that we want to do like this lah. Okay. So now you have two unknown here. So let me put this thing over there. So you have two unknown here, X and Y. And then you have this, what we call 1, 2, 3, 6, 5, 6, 7, 1, 2, 3, 4, 3, 4, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 12. I need to organize first. Okay, so these two things coming from this. So as you can see from this, wait, I need to put down. As you can see from this, first we want to check the melting point for this. Okay, because we want to find, we want to check the melting point. Okay, so we want to check melting point for this. Let me clean that first. It's quite messy now. Where to put? Okay, here. Okay, so in previous live stream, I've shown you this apparatus. This apparatus over here. So this melting point apparatus. So the idea is that we want to check the melting point for this. Okay, first, what is melting point? Question. What is melting point? What is the definition of melting point? Anyone? Say your name and answer that. What is the definition of melting point?
The temperature range of the substance.
How to know the range of melting point? Anyone?
Sir?
Alif.
Alif. Give Alif first lah. Alif.
How to know?
How to know the melting point range for particular substance? For example, let's say I have this egg here. How to know its melting point?
We need to see when is the first time of the particle to start melting, and then the last time of the last particle to melt.
Okay.
Finally melt.
Yeah. So that's correct. So normally we use this. We use this, and then we put it on this what we call this tube. This tube you have seen before. I will not go in detail on that because we have the live stream on that. So basically there are tube here. This is all it's not like a straw because it's both end is closed. So I will not go in detail. You can check the melting point what we call melting point live stream for that. So let's say now I want to put this X into this tube. So because this double end is closed, so I need to break it. Okay, so I break it in the middle. Okay, I break it in the middle. So I put somewhere here, and then I will open the X. So remember, this is X. This is X. I will do together, but we start with X first. Okay, so I will zoom it first because it may be quite far from you. I don't know where. Okay, so this X, and then I will take this capillary tube. We call it capillary tube. Okay, if you remember previously we talked about capillary. So because it's small, we call it capillary tube. Okay, capillary typically the term capillary is normally reserved for something that is hollow and small, like your capillary in your body. It's small and it's also hollow. It's like a tube. So I put some of it inside this, and then put some of it. If you have any question while I'm doing this throughout this TLC, you can just ask lah. Quite difficult because I'm doing this. I need to focus. More. Because this is not really powdery, so it's quite big, so that's why it's quite difficult to put it inside. Okay. In the lab, in the physical lab, every of you will be given this opportunity lah to do this thing. But unfortunately now, during the COVID pandemic, what to do? We need to do whatever we can. So this is enough or not? Okay, wait, I put a little bit more. Okay, if you see here, okay, so that's how much you need to put lah. Okay, so on top of this, they are like a hole. So I put one. Remember, X in the middle. X in the middle. Remember X in the middle because I want you to tell me what is the melting point for that. So let's do for a while. So I put this. Okay, so this is why same powder, not same powder. I mean it's a powder. And we do the same thing using another capillary tube here. And then we take it, we do it, we take it, we do it. TLC itself is easy. I mean, not easy, I mean fast. It's not really long to do TLC. It just, before TLC, we need to do this melting point identification because you want to know this X and Y from what group. So that's the idea. To do melting point here is to know what group that is belong to so that you can narrow down the TLC. If not, you need to do the all 12 compound. As I said, there are 12 known and the 2 unknown coming from this 12. So if you don't do this melting point determination, then you need to do TLC for all 12, which is quite a lot lah. So that's why the reason they are melting point. So you need to be careful. Okay, let me put a little bit more. I think that's enough lah. If you think about it, TLC is just like that. Just put in the put something on the what you call plate or whatever TLC plate. This is a tissue paper, and then you put some solvent and done. So that's TLC actually. Okay, so now there's quite a lot, but it's okay. So you see there are another one. Okay, so let me put on this thing on the left. Okay, on the left. Okay, so remember the middle is the X, the left is the Y. Okay, let me clean this table first before I show you. Your task now is to find the melting range for this. So this basically the question also lah. Whoever first tell me what is the melting range for X, get the mark. Whoever first tell me what is the range for the melting point for the Y, also get the mark. Okay, for this I need to zoom out. Banyak betul control. Okay, zoom out detail. Okay, so I do like this. The detail you can see in the melting point live stream, but I need to change the camera here. So this camera on top of this, I need to change so that you can see here lah. Okay, let me change first. So let me open this thing first. Okay, and then what one nak change? Aku lupa macam nak change. Macam ni kot. Macam ni ke? Macam ni kot. Itu dia. Okay, let me adjust. It takes time a little bit here, so bear with me for a while, because I have only so much only a few webcam, so I cannot have this fixed to some else. So I think this is just this one. Let me zoom first. Okay, you get that image, and then I need to have another image for the control panel. So I need to bring this. Oh, this is quite far. Let me bring here for a while. Okay, I need to bring this quite far here. Okay. Later I will zoom this, but I need to change this to something where is it? Oh, I need to bring it a little bit far lah. Okay. Okay. So where is it? I need to bring it further. Okay. I hope you can see this thing. Okay, as long as you can see this, what we call the this is quite far because I don't want to move this thing. Wait, it takes a little bit time to adjust this thing. But bear with me for a while. What's important is just this. It's just the what we call the number. Can you see now the number here? Is it clear, the number? Can you see or not clear? This number first.
Blurry.
Blurry, yeah. So let me focus for a while. This thing I need to focus. Let me make bigger lah. This one I make it bigger a little bit. Sorry, I have to do a little bit control there. Yeah, you can go there. Okay, so I just here lah. Okay, that's the thing. So is it clear now the what we call the number here? This thing first. Is it clear or still blurry?
Yes, clear, sir.
I think clear, right? You can see now 29.7. So I think that's clear. That's the most important thing lah, because I don't want to waste more time to adjusting this and that. Okay, now I want to check this thing first. Okay, let me zoom this first. Okay, let me zoom. You have the reflection from the light above. Let me zoom this first. Okay. Zoom. What is the thing? Okay, you see this is the middle one. So I go down. Go down. Okay, so let's go down. So this one is the Y. This is Y. The middle is the X. So I go down, go down, so I go down. So I put a lot more, but it's okay. I think you can see lah. You can see lah. I think it's clear lah. When it's melt, you can see actually. I think, but the middle one is. Let me remove this color jap. Oh wait, no, I forgot. Let me. Okay, so this is the middle one. Let me put the middle one first. Okay, so this is the middle one. This middle. Okay, so that's middle. You can see. Can you see that? Is it okay? The focus, is it okay? The middle one. There are a lot of debris on top of that, but I think you can see the what we call the middle one. The compound in the middle one. Is it okay or not?
Okay, sure.
Is it clear? So this is X. This is X. So let me put the Y. So this is Y. So this is Y. So the Y is quite full. So I put a lot. But it's okay. I think it's okay. Okay, I think you can see. So now the idea is this. I will ram this thing. Okay, now I will put it around 60. Okay, because if you look at our table 2.2, I don't want to move this camera again. But if you remember, table 2.2, there are 4 groups. Okay, there are 4 groups. So the minimum, the lowest temperature for all these 12 is around 65 something. So I will set it to mode. I will set it to plateau 60 because our lowest temperature in all this group is 65. So I put plateau 60, and then what else? Slope 5 degree per minute. So in 1 minute they will increase in 5 Celsius, and then cooling no need, and then a plateau. Okay, I think that's it lah. So I can press start. Your task now is that to check what is X, what is Y, the melting point for X and Y. Okay, 1, 2, 3. Okay, now it's heating. Okay, going to the plateau is heating fast. Okay, so the 5 Celsius per minute happen after you reach the plateau that is 60 that we set before. Now it goes very fast, 32, 33, 34 like that. Oh, you can still see me. I think. Oh, there are camera over there. So while you doing that, let me prepare other thing lah. So you do this thing. Whoever give me the what we call the melting point for X and also melting point for Y. I mean different person. Whoever first tell me that, then get mark lah. So now it's going to plateau 54 something. Now it's going to 60. And when it reach 60, it will give you this beep sound. Normally doing this is take more time than the TLC itself. But because we want to narrow down the compound group, then we need to do this. Okay, so that's the sound. So they ask you now, now it's steady at 60. Now I will start ramping it up by clicking the start here. Start. If you got your lab manual with you, it's better lah. So you can sort of like gauge which group they are.
Sir,
Yes.
the X is from group
Give your
2.
name.
Hannah
Hannah. Okay. So X is
from group 2.
group 2. Okay. So remember X is from group 2. So now we want to find Y. Hannah, later on you give me what temperature range?
81 to 83.
81 to 83. Okay, later I will put it, write it on the ni lah, table that I have. But now we are waiting for Y.
Sir,
Okay, name.
this is Nur Sarah.
Sarah, yes.
Why it is from group 3?
Group 3. Okay. Okay, so we basically done. So both of it is already what we call melted. So now I can stop this thing. We can stop this thing. Stop. Okay, so I just now I rearrange this thing. Okay, let me give down. So let me show first this thing. I need to readjust again. So that's the thing, you need to readjust. Readjust. Where is my, yeah. Let me, okay. Okay. So let me make it smaller, this thing. Smaller, and then I will zoom in this thing. Okay. And then I will bring this whatever apparatus here over there so that I get more space. Okay. And then now we have X and Y. Okay, you can see now here, but this is quite, they have like reflection. Maybe I can use black also. I don't know whether if I put black underneath black, is it reflect also? Same thing. Yeah, it's reflection from the light, so cannot do anything. Okay, anyway, now as you can see here, 1, 2, 3, 1, 2, 3 coming from here, and then 4, 5, 6 coming from here, and then 9, 8, 10 coming from here, and then also 7, 4, 5, 7. Okay, so this 6, 26, 1, 2, 3, 4, 5, 6, 26. Oh, this 6, 7, 4, 5, 6, 7, 8, 9, 10, 11. So basically it's like this. You have all this compound. Okay, this compound already put in this what we call this small jar, and you see on the group 1 here you have this one dimethyl biphenyl metabenzoate, and this group 2 you have this, group 3 you have this, group 4 you have this. So you can see this in table 2.2 in your lab manual. So because Hannah said that X is group 2 and Sarah said Y is group 3, we can remove this lah. So now we basically narrow down the Okay, if you look here, if you see here, if you see over here, even though Sarah, siapa nama dia tadi? Sarah, Hannah or Sarah, the first one, the X, Hannah.
No.
Okay, Hannah, you said melting point for unknown is from where to where? From what to what?
81 to 83.
81 to 83. And then, siapa seorang lagi? Sarah, the group
Yes.
3, from where to where?
94 to 96.
94 to 96. Okay, so this is basically we put this as X lah, as X, and then this will put as Y. Although here you sort of like got the idea where is which one is which one, but if you look here, the melting point is more or less near with each other. In reality, it's not as clear cut as that. Okay, they are like many compound because this is pure compound. Remember, this is pure compound, so melting point is sharp. In reality, when you want to detect the unknown, the melting point will be like larger range. For example, here, even though it's 81 to 83, you might say it's vanillin, but it might also be naphthalene. And it might also maybe nitro acetylformine, but have some maybe more pure or maybe there are some impurity. So that's why we put it in group, because we are still not sure. In order to sure in any research, normally you do cross check. One experiment normally is not enough to what we call to give you a result that people cannot argue. In order for you to get a result that people cannot argue, is that you need to cross check with another test. That's why we do TLC. Here, the idea for melting point is just to narrow down only. So we know from the 12, we sort of like know that we narrow it down to 6. Okay. So now from the 6, we want to narrow down it to 2 using TLC. Okay, so this is Y. So let me put this as a Y. It's a Y. This people confuse as X. So XY. So now we have this, and now we want to dissolve it. Okay, we want to dissolve it because TLC, in order to put something on this paper here, in order to put something on this paper, you cannot put powder or this solid because it will just run off. You need to stick this thing into this. So you want to make this as a solution. So the question now, what will be used to dissolve this thing? Okay, what is to be used? Let's say I give you the you have ethanol. Let's say you have dichromatin, you have ethanol, and also you have hexane here. You have hexane, you have ethanol, and also dichromatin. So which one you think that will be used to dissolve all these 6? You have ethanol, hexane, and dichromatin. This is question. So anyone?
Alif.
Name?
Alif.
Alif.
Jahan, sir.
Jahan first lah. Alif you done just now, right? Jahan first. Okay, Jahan, which one?
Ethanol.
Ethanol. Okay. So actually is all of these can do that actually. But ethanol is you can dissolve all of this in ethanol, but maybe it will not fully what we call fully dissolve, because remember ethanol have OH group. Ethanol, you have OH group, so it's more like water. So if you have organic compound normally doesn't dissolve in water. This let's say you have this just now at the beginning I show you this pen. This is water based, meaning that you can use water to dissolve, so that you can see now here it's already disappear. Anyway, so this is water based, water can dissolve it. But if you have permanent marker, like this, I try to put a dot there, and if I use water, then it cannot move, because this is normally this is non-polar lah, because they make from whatever they call, I don't know what they make of, but basically because water cannot dissolve this, then we can say it's more or less towards non-polar. Ethanol is like water, because ethanol is not like water, but you have OH group. Okay, you have OH group, and water also OH group. It is like polar lah. although it's less polar than water. Okay, most of the organic compound normally cannot dissolve in water. So usually you need something that is non-polar, because water is polar. If you want to dissolve this, you need to use something that is not polar, not like water. So like dissolve like. So that's the idea lah. So you need something non-polar lah. Ethanol can, but maybe just very small amount lah. Okay, very small amount will be dissolved in ethanol. So you can use either hexane or dichloromethane. Hexane and dichloromethane, both of them can dissolve this lah. But for this purpose, we use dichloromethane. Here, if you see under the what we call, where is the thing? Okay, dichloromethane is more or less like this. Okay, you can see here. I don't know what you can see. So dichloromethane is basically you have C and then you have Cl and then you have Cl, and then you have H and H. Okay, so this is dichloromethane. Color like this. Okay, so that is basically dichloromethane. Okay, so we call also this dichloromethane as methylene oxide lah. I put it here, it's much easier. Okay, so this dichloromethane. So we call this dichloromethane also DCM or methylene chloride. All the same name lah. DCM, methylene chloride, dichloromethane, all the same name. So if you look here, there are no OH group. So that's why it's non-polar. Hexane is basically, you learn in organic chemistry, you have hex, so meaning that you have 6. So basically you have C, 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 let's say C, C. So basically that is hexane, 1, 2, 3, 4, 5, 6. And then you have H lah, H, 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 and so on. H, 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 H. So this is hexane. If you look here, hexane also doesn't have, I don't know whether it's clear or not. Okay. If you look here, hexane also doesn't have OH group, so it's non-polar, so it can dissolve whatever here. But for the ethanol, then you have OH group, so that's why it's better to use something like this or this to dissolve our ni lah. So we will use DCM. Okay, so to do that, we just take this. This basically we want to dissolve only. It's not mobile phase. It's just we want to dissolve it. So let me put here, and then we take X, 1 beaker, 1 beaker. So because we know the X, so we have X here, we want to put some of it inside this. Okay, we want to put some of it inside this. Okay, so we have X, and then we have X, we have this. So I just do it fast here. So X, I just put just a few gram of it. I just put there. Okay, just put a few gram of that, and then I close it, and then I do Y. And when you want to do Y, don't use the same spatula lah, because it will contaminate. TLC is very, what we call, very sensitive, so I use a different spatula. So I go Y, and then I take some of it. I put that, maybe some more, a little bit. Okay, so done with Y, XY. Okay, so done with that. So now I want to dissolve it. So I will be using this what we call this pipette there, and then dichloromethane. We have dichloromethane over here. So this is dichloromethane. So I will open it, and then let's say we want to dissolve how much? Let me check here. If we see, we want to dissolve around 2 ml. Let's say we do 3 lah. We do 3 ml. So this pipette can take up to 10 ml here. You can see this 10 ml. So this pipette can take up to, I don't know whether you can see or not. Yeah, I hope you can see. Yeah, can go to up to 10. So we just want 3 ml. So you just go 3 ml, and then I take the pipette tip here, and then I do the thing, and then I open, and then I just go. So that's 3 ml. So that's 3 ml. And I put on X. And also I put on, because you use the same solvent, it doesn't matter, you use the same pipette tips. Okay. Once you do that, then I put somewhere here, here, close that, and then you sort of like this. So let me zoom a little bit. Where is it? Okay, let me zoom a little bit here. So if you see here, it's already dissolved lah. Dissolved. I mean that there are nothing inside that. If you use water, it will not do like this. You still see a clump of powder. So because this using the organic, you're using the non-polar solvent, then it will dissolve like that. Okay, so that's one X, and that is Y. It's important for you to label. It's important for you to label. If not, you don't know which one is which. So X and Y. If you look here, both of that is colorless. That's the reason why your TLC need to have this fluorescent. If not, then you cannot differentiate which one is which. So it's colorless. Okay. So if you look at your here, our what we call our flowchart, you done the dissolve here. What to do now is to prepare the TLC plate. Okay, prepare the TLC plate. We will do a line here, top and bottom. Okay, the idea for this is that you want to know where it start and where it stop. So that's the reason, so that you can sort of like standardize everything. And you will put plate 1 will be X is unknown, and then plate 2 we put X and A, meaning that whatever in the group, let's say you have 3 things in the group, so A, B, C, you add with you what we call, you combine X plus A. Okay, this is what we call co-spot. Okay, and this A is basically your known. So basically the idea now is you want to compare what happened to X and what happened to your known sample. If the X and A give you the same height, for example, later on it will move, go up. If X and A will move somewhere, X will move somewhere. Okay, this is combination. If let's say later on you are dealing with a different compound, you will see a two spot here. Two spot, because it's not the same thing. So that's the idea for this. So in order to do this, you can see that for plate 2, we need to prepare like 4 plate, but I just do only 4 until 3 lah, because 4 is just a validation only. So I will do only plate 1, plate 2, plate 3. So the idea for each plate is that I compare plate 1 for one of the known compound in that particular group, and then plate 2 another compound, the second compound, and a plate 3 for the third compound. So we will do this thing. Okay, let's go that. So we put this thing on the side first, and then we take our here this thing. Okay, so we will mark the what we call this TLC plate. Okay, so TLC plate. The way how you mark it, you use pencil. You use pencil. Don't use pen, because pen, remember, pen have ink, and ink also we can say is non-polar lah. So later on when we use solvent or any mobile phase, that the ink also will be separated. So you don't want that. That's why you use pencil. So pencil have carbon in it, so it doesn't matter. So how you do it is just you measure 1 centimeter from the top, from the bottom, and 1 centimeter from at the side. Okay, you can see, right? You can see I doing. Okay, you can see. So meaning that you do like just like this. Okay, like that, and then like this, like this. Okay, so you do like this. So now this become like the bottom, this become the what we call the top one. This become the bottom, this become the top one. So the idea is that you want to spot on the bottom here. The bottom here, you want to spot here. And then similar with this one, you need to put the spot above than whatever later on we will put underneath it. So that's why we put this mark, this 1 centimeter. So that if we try to test different compound, then we get the standard lah, standardize everything. So that's the reason for that. Okay, and then after that we just put this whatever our thing here, and then this is our front lah. And this active site is quite flaky. You see here, I don't know whether you can see. Yeah. Okay, yeah. Okay, so here is quite flaky. If you think this is quite flaky because it's just, yeah, you see. Can you see that? It's flaky here because this is silica. So that's why you don't touch the active surface. You hold it by at the side like this. So that's how you do it. And because to save time, I already make it here. So I make some of it here, a lot of that. So now what I do is that I will put the name lah, because now we know that we are only interested with what we call which compound. We only interested with this thing only. We only interested with group 2. Oh, this is not. Let me check first. We only interested with group 2 and group 3. So we just remove whatever not needed. So group 2 is 4, 5, 6, 4, 5, 6. So I just put here so that I do not make a mistake. 7, 8, 9. So here, and then we just want. So this is known, known sample. So this I will put over there so that I'm not messing it around later on. Okay. Okay. So you have this thing, and now we will mark first. Okay. How we do it? So let's do for group 1, 2, 3. So let's say this is for group 2. So let's say this is for group 2. Okay, this is group 2. We just do 3 plate only. So this, let's say we put it X because we know X coming from group 2. So we do one by one lah. So 4, 5, 6, 4, 5, 6. So this one, 4, 5, 6 here. So you see 4, 5, 6. So basically this, we know that the X coming from this group 2. So we put here X. I will zoom it so that you can see. Okay. Okay, so I will put it X, and then in the middle I put X plus maybe. So in group 2 they have 3 nitroacetophenone. So you put 3 nitro like that, and then this is 3 nitro. So just get the idea lah. Okay, so that's one. And then this number 5 also in group 2. The name is naphthalene. You can see, naphthalene. So I put here, X, and then in the middle, X plus naphthalene. Okay, and then the last one is naphtha. Okay, so you can see here, that's how I write it using the pencil. It's important to use a pencil. You see it? Okay. Okay, I think it's okay lah. Okay, so that's how. Okay, so that's the thing. Similarly to the last compound is vanillin. Okay, this is basically vanilla. So do the same thing. So I write it here. So this is X, and this is X plus vanilla, and then this is vanilla. Okay, so that's how you do it. And now we're done with the group 2. We now do for group 3. So we put it aside. I will put aside, and then this is group 3, which is also 3 compound. You have this benzyl, you have the acenaphthene, and also methyl 4 nitrobenzoate. So again, we do the same thing. So I take this 1, 2, and 3, and then same thing. But because now this group 3 correlate to Y, not X, so we do the same thing as before, but now we do Y lah. So we put 7, 8, 9 here. So maybe here we put Y, okay, Y, and then this Y plus acenap, okay, and then this is acenap, okay, and then here the second we put it Y, and then we put Y plus here benzyl, and then last one is benzyl. Okay, and the third one is Y, and then this Y, and then Y plus methyl 4, methyl 4, and then the last one is methyl 4. Okay, so basically you're done now. You're done with the naming this thing. But also in order to check this, all this, what we call all this, okay, in order to check with all these two group, you also need to dissolve this group. Same thing as before, we just dissolve in the dichloromethane lah, because we want to fix it on the this thin layer lah. So now what to do, this I put it on the side first, put on the side, and then I try to dissolve it. Okay, I try to dissolve it. So now I have done this. I have prepared the what we call this thing. Okay, I have prepared the flask, and each flask have already have the label on it. It's important to label because everything is colorless later on. So now the same thing, you have this. Let's say do group 2 first, nitroastaphene. So nitroastaphene. So let me this is naphthalene, this vanillin. Okay, so now we can go to this stuff lah. So nitroastaphene. So as usual, as before, just take some only. This one you already know what is it. Previously we don't know. We just do for X. Why is so difficult to take? Okay, any question until now? Okay, I give you the question. Ask me question. Ask me one question. So whoever ask question now get some mark. So this naphthalene. One, two. Can you see? It's okay, right?
Yes, I can see.
That's the problem, this online thing, because I don't know whether you are still there or not. If you are in the lab, then I know you are in front of me. So yeah, but we manage. It's okay. Vanillin. Okay. So that done. Now to save time, I do also straight for this for another group 3. So I take another one. Okay. This is acetate, methyl, and benzyl. So acetate. So acetate. We take one there, just a little bit, because TLC is quite sensitive, so you don't need a lot. So this one, and then this, and then benzyl. Also this benzyl, you see the color is yellow. Okay, just a little bit, like 1 gram, 2 gram. That. Okay, every time you want to take the sample, I use a different spatula, because if you use the same spatula, then you have 2 compound then. So this is methyl. Let me put a little bit more. Okay, so we're done with that. Okay, so if you look here, I just use a little bit only here. You can see lah, I use a very little of each compound. So now we can put everything here somewhere else so that we don't knock it off. So now we take dichromethane, take it, same thing again, we take our anise, and then because it's used DCM only, so we just use the same tips, and then we just put 3 ml for each. 1, 2, 3. Actually, it's very hot now. There are no aircon. Because it's Sunday, the unknown aircon. They don't on the centralized aircon. And also I wearing this lab coat glove. Quite hot. That's okay. So this here. Okay. So we're done with that. Okay, so we close first before. So now we swirl it to dissolve it. Okay, just swirl it like that. Swirl like that. Swirl like that. So now it's already 10. Okay. If any of you have like data problem, you can lah, because as I promised, if you have it's already 1 hour and a half. Maybe after this, just putting on the TLC and visualize. So maybe another half an hour. I don't know, half an hour, 40 minutes like that. But if you have like data problem, then you can go lah now. But if you want to claim a mark, if you still have nothing to do, then you can stay and until the end. Because now it just ready everything. So you have now this 6, this group 2, and this is X. Remember, this is X. Okay, this is X. This all group 2 known. Okay, so this is Y. So I put it in front lah because my table now is quite messy. Okay, so now you see. So this is X and this X coming from any of this. Okay, this is group 2. This is Y. This is Y. So this Y coming from any of this group. So now we want to put this on our TLC plate disk. So in order to do that, we need to something to pick a drop only and then transfer to this TLC plate. Previously, we used this green marker because it's already a solid. Then I can just write on the this lah, on the what we call on the tissue paper. But now it's a liquid now, so you need a method to find a way to transfer this liquid, just a little spot, into on this TLC plate. So we do that using this. Okay, using this same thing as a what we call our melting point, but we need to adjust a little bit because we need not as this big. This is still big. If you see, this is still big. We want just a small drop only. So we need to adjust this thing. So how to do that is basically, I put here, I put here, I put here. Make sure everything is labeled when you do your work during FYP later on, because maybe now you cannot come to the lab, but later on, 2 years, 3 years from now, I hope that the COVID already settled and then you now get chance to work with your hand. So you need to remember the very important thing for lab is that labeling. You can make all the stuff, but if the label is wrong, then your result will be messed up. So that's one thing. So how to make smaller, let me zoom a little bit. Okay, wait, zoom. Okay, so this is quite small, but in order to pinpoint here, to make a point, alamak jatuh. Wait, Okay, in order to pinpoint on this film, we need a very small drop lah. Because if you look here, okay, if you see here, okay, we're done with this, prepare TLC plate, we're done. Now it's number 3. We also done with the preparing the, what we call the solvent here. Now we want to drop on the TLC plate. We need a very small amount of it because the layer is already thin. Remember, the silica on the support is not much, it's just a little. Okay, you just need a very small spot. So you do that by using this capillary tube, but you need to adjust it because this capillary tube, wait, let me change. Because this capillary tube is still big for that. Okay, this capillary tube is still big for that. So to make it small, we take this Bunsen burner, okay, Bunsen burner, and then we make a pull out of it. So I open this Bunsen burner. So I need to be careful because above it is camera. I will make it the air coming in because we want the blue flame, so that When air is enough, then the combustion is complete lah. But where is the thing? That's the thing. So that's the thing. So I need to go a little bit side because I don't want it. Okay. Okay. Basically, there are fire there. I hope you can see. Okay, there you can see. Okay, there are fire there. We want a blue flame. So in order to get blue flame, you give air a lot there on the side. So now we have this capillary tube. So how you do it is basically you put in the middle here. So I will put in the middle there, and then it will sort of become saggy, and then you pull while doing that. Okay, so let me zoom a little bit so that you can see. So I hope it will not burn my. Okay, still hot. So I need to be fast. So I put on top of that, and then after you see it become melting a little bit, and then bring out, and then you pull, and then hit it, pull like that. If you pull too fast, it become like a sharp end. Okay, it becomes sharp end if you pull too fast. So you need to find a way, just pull it just nice. Okay, again, one more. Okay, so I put here. Okay, hit it first, and then pull it. Okay, okay, it's okay. It's okay. Okay, so I need to close this. Okay, because it's hot now. Okay, so if you look here, you have this capillary tube pull so that the middle becomes so what we call so smaller lah in terms of diameter. So now that diameter is what we want to suck the liquid from this our known and unknown. So you have this capillary tube, and then what you do now is basically you break in the middle lah. You break in the middle like this. You break in the middle. Now you have sort of like what we call. You have. I hope you can see. Okay. You have two capillary, but with smaller diameter end there. Okay. So we will use this end to dip into our what we call our liquid, and by action of capillary action, yeah, it will suck the liquid. Okay, but the problem now, this end is closed. You cannot suck if it's closed. You need the capillary action works if both end is what we call both end is open. This one is closed. This one is closed. This one is closed. So you need to break this thing. So I bring this thing, what we call this plier. So I will break that thing. So let me. Okay, I will break that thing. But because this end is very difficult to break using hand, and also it's bigger than this, when you try to use this plier to break it, it will shatter. What we call the glass will shatter everywhere. So it's important for you to have some sort of like ways to prevent that shatters from going to all the place, because sometimes it can goes to your chemical, and sometimes can also goes to you, your eyes, and so on. So that's why it's important during the lab. In the lab, you need to wear the glove, wear the eye protector. I'm using glass, so it's okay lah. So now I will break it inside this plastic. The same thing I will break inside the plastic. So the same thing, basically I just break here, but I do it inside the plastic. Okay, and then the other one inside the plastic. Okay, so now done. Okay, we put the plastic away, and You see now. Okay. See now we have two now. We have two. Let me zoom a little bit. Okay, we have two things now. We have two things. Both are open because we already break this part. Okay, this already break here. You can see that's already break there. Okay, that's two part, and also this is part that is smaller lah. That is, where is the zoom? Okay, okay, that is smaller on the other side. So we use this part to dip our liquid, and because we have this what we call, we have we have around what we call, we have around, okay, we have 1 2 3 4 5 6 7 8. We need to prepare more lah, but I already prepared that. So I already prepared that thing. Okay, I already cut and prepared that thing, so it will save a lot of time there. So now we have the spotter. We call this as a spotter. So we call this thing as a spotter. So now what we do is that, let me close this first. Okay, what we do is that we want to put like this. We want to do like this. Plate 1, plate 2, plate 3, plate 4. Meaning that for X, you have what, 3 plate. We don't do plate 4. We have 3 plate. Plate 1, plate 2, plate 3 for the X, and plate 1, plate 2, plate 3 for the Y. Okay, so we do that. We already write our thing here. So we start with the X first. Where is X? X, X. So here X, and here X. So here X. X, we start with acetonol. X, 3 nitro, vanilla. This is naphtha. Okay, so this is our X. So the way how you do it, let me put here a bit. Okay, so I can bring this over there, this here. Okay, so now here already they have I already marked this thing. You can see previously we already marked this thing as X and X plus whatever, X plus whatever. So now we want to spot it on top of that. So what you do, take X and then take the spotter. So this is the spotter that I just did before. And then you just try to take it lah. Just try to take this X. And because, okay, one way, one tip is that when you want to do this, because you know this X, this X, this X, you can do straight away. Okay, you can do X, X, X straight away. Don't need to do again and again. You don't need to finish this first and then next here. You can do straight away here, all X. So that's what I will do. Let me show a little bit nearer so that you can see how to spot. So that's the nearest lah. That's the highest zoom that I can use. Okay. So just take a little bit only. You need to tilt this thing a little bit. Okay. By doing that, it's already sucked some water. If you look here, yeah, it sucks some liquid lah. Your sample. Okay. So we just want a little. So you just put a little bit there on top of that. Okay. Just put a little bit. Oh, that's too big. This is too big. Okay, this one is too big just now, but it's okay. Okay, that is a way of itulah. This I think I know maybe. And also because in the middle also X, then we can put straight away lah in the middle. Okay, in the middle you can also straight put the X there. X in the middle. X in the middle. X in the middle. Okay, so you have this X. It doesn't matter now we do again because we only have X here. Okay, so it doesn't matter, it's not contaminate the thing lah. So basically we're done with that. So now we want to see, now this spotter you cannot use again lah. For the next you need to use another spotter. So I put that somewhere else lah, that spotter. Now we use next spotter to put the nitro, okay, the nitro. Okay, so now if you see here, M nitrophenan here, you can see on the side here, they are, it's alone, and the other side is combination with the X. So if you want to, what we call to spot, you spot here first, when it's alone first, and then you on top of that. Because when you, if you spot in the middle first, then it will contain. Okay, we want to minimize the contamination and then also to minimize the use of spotter. So that's why now we take the another spotter, this new spotter, and then as usual we take this and then repeat. So actually that's TLC, it's not really difficult. So put here first, that's one, and then I don't know whether it's clear or not from your side, but I hope it's clear. So here I want to put another one in the middle. You don't need to put a lot, just one drop enough. Not one drop, even smaller than one drop. So I put here. Okay, so this is basically what I call co-spot. You are spotting on the same place where the previous spot. So now this thing become like a mixture. In the middle now become a mixture of compound. If the mixture, if the middle is the same compound, then it will give only one spot lah later on. If this is made of different compound, then you will see a different retention later on, different spot later on. So we're done with this. Now we use a new spot. So we take a new spot and prepared before. So now we're done with this thing, and then we use naphthalene for the second one. So same thing. It's not really difficult. So just put here. Oh, that's too big, but it's okay. And then I want to put the middle. Okay, so that's okay. So it's already combined there. So now done with that. So we continue with the last, which is vanillin. Okay, this is vanillin. So take a new spotter. So I take a new spotter now, a new spotter, and then do the vanillin. Okay, so I do the vanillin here. Okay, that's enough. And then maybe here. Okay, that's enough. Okay, once you do that in the middle, you cannot put it back again because it will contaminate the thing. So we done for the X. Now the same thing we do for the Y. So this is Y, this is Y, this is Y. Y first is acenaphene, second is benzyl, this is nitro. So I will bring this X somewhere else so that it will not disturb my table. Okay, so this I bring up, up, up. Okay, so now that's Y. So this is Y, same as X. We do Y for all the three plate first. So take the new spotter. So I take a new spotter here. So this, in the lab, in the actual lab, you need to create each spotter and so on. So it will take a longer time than this. Even though you think this is long, because you just watch it in front of me. But if you try to do it, it will take quite a time because you need to be careful not to take a lot of here. You need to prepare this, need to label everything. So in actual lab, normally it takes longer time than this. So this is Y. So I put Y as usual. Put here, and then take one. And then I put here Y. And then I put again here. Y here. Okay, and then I want to put in the middle. In the middle. Okay, then. Okay. And then here. And then lastly is here. Okay. So now we have all Y putting on, we already put spot the Y, we call it spot. We already spot all the Y compound on this TLC plate. Now we done with this, what we call this spotter, we put away. And then now we do for each of the compound in the group 3. So the first compound is aceton, what we call it? Acetonaptine. So this acetonaptine. So we just take one. So we put here. Okay. And then the second one in the middle. So it's mixed with the Y. If the Y is acetonaptine, then it will give the same result lah. Okay, done there. So now this we done. We put away. Another spotter. Another spotter for benzyl. So now you have benzyl here. So you have benzyl here, and then we put it on top of that. Okay. So we put here. Okay, and then in the middle. Spot that. Okay, so that's done for benzyl. And then lastly for methyl 4-nitrobenzoate. So this methyl 4-nitrobenzoate. So another spotter, the last spotter, and then wait, I take it. Okay, this is another last spotter. So we take it and then do as before. Okay, so we just spot methyl here first. Okay, and then the last spot that we do is here in the middle. Okay, done. Okay, so we done with all this, what we call, let me, this thing. Okay, so we done with all these things, whatever material here. And we also done with spotting on the TLC plate. So now what we will do is that we want to develop the plate. Okay, so now we are done with this part 3. Now we are going to part 4. We want to create this developing solvent. Previously with the green what we call green marker, we use water. But here we will use solvent lah. Okay, the reason behind that and so on, you need to refer to your organic chemistry lah. I can explain, but I afraid that it will take longer time lah. So basically the idea is that different solvent have different polarity. So it will affect how far and how far the solvent will keep the compound on the TLC plate. So basically here, if you look here, you can see that they are for group 1, you need to use this solvent. Group 2, you use this solvent. Group 3, you use this solvent. Group 4, you use this solvent. So we are doing group 2 and group 3. So we are using this. CH2Cl2 is basically DCM lah. Methylene chloride or dichloromethane. The same thing, the same name. So we put 9 part of dichloromethane and 1 part of the hexane. We combine them together. Okay. So we know the hexane is non-polar. The dichloromethane is basically, the polarity is in the middle actually. I mean, they are not totally non-polar. Hexane is more non-polar than dichloromethane. Okay, so here we have hexane group 3, we have hexane mixed with the ethanol, 9 part of hexane and 1 part of ethanol. Ethanol being polar, hexane being non-polar, so you get like a mixture of polarity lah here. We prepare this thing 10 ml in the flask, and then we will transfer 5 ml into this developing chamber. And then later on, we will put our TLC plate on the chamber, and then like our tissue paper and the green dot is the same thing, and we will see the thing lah. So now let me change here. Okay, so now what we will do is that we can remove all the non-use, all this thing away, so that it will sort of like give me more space to work with. Okay, let me move this thing. Okay, so now you have this, and then what else? We want to prepare the, what we call? We want to prepare the developing solvent. So by the way, now is basically drying. The compound that we just spot on this thing is what we call is drying now. It's drying now. Okay, so now for here, this part, we need what we call the solvent is basically I conteng sini lah. Is 9 part over 1. So this is DCM and this is hexane. Okay, so that's what we do here. Okay, so don't worry scribbling on the table here, because you can use acetone or ethanol to remove this. Whatever acetone, you can normally use acetone lah, because this is this whiteboard marker is basically it's not non-polar, is a little bit polar, little bit non-polar, so you can just use whatever dissolve, not water, you can just ni lah. Okay, so now we have this. We want to prepare that first. So we want to prepare 9 part of DCM and 1 part of hexane. The total should be 10 ml lah, to make it easy. The total I will do it 10 lah. So as usual, we take this thing and then we take the DCM tips and then we connect it and then we set this thing into, because we want 9. So we go to 9. We go to 9, 4, 5, 6, 5, 7, 8, 9. 9. Okay, 9. And then now we take dichromethane here. This dichromethane. We open it and we take 9 part of that. When you use pipette, please make sure you, when you want to try to suck thing, make it very perpendicular lah. So, and then we start the thing, and then you see the again. Okay, so I have this, and I will put inside this. Okay, so we done that, and then we put our type hit that. It's important when you do any lab, you need to be relaxed. Don't kelang kabut, kelang kabut apa? Don't become too ni lah agitated or what is kelang kabut. You just may relax. Okay, hexane. We want hexane. So we have another pipette tips. Okay, so we take hexane. So we have hexane here. So this hexane, and then we take it hexane. And then hexane is, we need 1 only. So don't forget to change this. So go to 1. 1. Okay. So we take 1. And then that is the mixture. Okay. So that is the mixture of DCM and hexane. Okay. So we done with that. This is the mixture. Okay. So that's, I put there. I put here. So now for this, for another one, we need what? We need hexane. We need 9 here and 1, but here 9 is hexane, and this one will be ethanol. Ethanol. Okay, same thing. So this is for this, and then I take another. Okay, we take hexane here. So 9 part of hexane. So because this already 1, so we just go ethanol first lah. So we just go for ethanol first. So this ethanol. So I go open the ethanol and take the tips for ethanol. So I already prepared the tip for ethanol. And then I take some of ethanol here. Let me take it. Okay, I put ethanol inside that. And then we done with that. So now we want 9 hexane. So just go to 9. 4, 5, 6, 7, 8, 9. 9. Okay, 9. And then we take hexane here. So hexane, we take hexane. We take 9 there. So take the tips, hexane tips here. And then we attach it. And then we take 9 ml of hexane here. So this 9 ml. And then we put that. Okay, so now we're done with this, what we call, with the all this chemical. So we put away. So now in front of you now, we have these two mobile phase. Previously we used water, but now we use the combination of polar and non-polar. The way how to get that, why is 9 to 1, 9 to 1, is depend on trial and error. In your lab manual, you will see that it's a little bit different. Not little bit, a lot different than this, because when I try using whatever in the lab manual, doesn't get it. We cannot get it lah. So sometimes you need to modify. So this is a solvent, the mobile phase that we will use to push our sample on the TLC plate now. Okay, so this mobile phase is used to push whatever on this TLC plate now. Okay, so what to do next is that we want to put this into a developing chamber, because I cannot put this inside, because this is square, so I cannot put inside. So we have what we call developing chamber. So this is what it look like. So this is what it look like. This is developing chamber. Okay, developing chamber here. So it's basically, if you look here, there are like a groove there. So it's easy for you to put what we call the paper thing, film there, and so on. That's why the technician, they cut this, pre-cut this, what we call this paper, TLC, at this size, so that it can fit in this TLC, the developing chamber. So now, because I already put the, what we call the label there, so I can put this here, inside this. You might ask, why not I do it straight away here? Okay, why not I do it straight away inside the developing chamber? Because no reason actually. You can do that actually, but you cannot. This is 10 ml. This 10 ml. Oh, the reason is because this is 910, 91. So it's easy for you to use 10 ml. But if I do it 10 ml here, the problem with that is that the level of what we call of my solvent will sort of like above this line. So you see here, you see on the side here, if let's say your solvent level here is above, is higher, then you will dissolve the entire compound. You cannot separate. So that's the reason why we do this first, so that it's easy. It's 9:1, so we put like ml, so you get 10 ml, and then only then we put a less amount here to here. So I will put 5 ml into here and 5 ml into here. Okay, so because this is for DCM and hexane, then I will take new tips here. Wait, I take a new tip. Let me take a new tip first. Okay, so we want 5 ml, so just go to 5. 7, 6, 5, 5, 5, 5, 5, 5, 5. Okay, 5 ml. And then we take a new tips, because now this is combination. Previously, we are putting different solvent separately, but now it's combination. It's different thing. So that's the thing that you need to be aware when you do thing in your lab lah. You need to be careful. Everything that you do must have a reason. If not, then you can mess with the result. So this 9:1, so I will put 5 ml from here. So swirl. So I take 5 ml from here. Okay. Okay, so that is one solvent. Okay, and now we need to close it. The reason why we close it is because this is easy to evaporate, so you prevent the evaporation, and also at the same time you want to saturate. You want to saturate the vapor inside this, because it's evaporate, so there are vapor So by closing the lid, you sort of like saturating this developing chamber with a vapor of this solvent. So now the next one is this. So this is hexane and ethanol. So another new tip here. Again 5 ml. So we open this. Okay, and then we take that hexane and ethanol there. Okay, so now we're done with that. Okay, we're done with that. So we close this thing. So now we're done with the preparing the developing chamber. So now we're already near to the end, because if you look here, we left with the last part here, developing the TLC plate and visualization. Okay. Okay, so I think now we can go straight to the next part. For this, I need to use this thing so that you can see lah. For this we need to do one by one lah. But it happened fast, so it's okay. So I will bring this first. So let me adjust this because I want to put the this thing here because you want to see from the side. So okay, let me make it bigger first. Okay, there. And then this, we're done with this. Enough. And then we will put our developing chamber here. Okay, here, maybe here. One by one lah. Here. Okay, here. Okay. Is it clear? Is it okay? Anyone? Is it clear here?
Yes, sir.
Okay. So now we want to put the developing chamber. You need to put it very carefully. So I need to put very carefully because wait, I need to adjust things. Because if not, it will splash. The solvent will splash, and when it splash, it will cause your compound to bleed. We call it bleed, B-L-E-E-D. So let me zoom this first. Yeah, let me adjust a little bit there, a little bit here, a little bit here. Okay. I hope that is clear. Wait. Okay, so now this is what we call this. This is this. Okay, this is this one. Oh, you cannot see here. Anyway, it's okay. This is for the X. For the X, there are 9 part of DCM, 1 part of hexane. So now I will put our paper there, thin layer paper there. So I'm using this, what we call this, what is this? Tweezer. Okay, we start with this first. By now, all this thing already dry lah. We need to make sure it dry first. So now you need to put it very carefully inside that. You need to put it one by one lah, like this. Oh, be careful. Okay. Okay. So I hope you can see. Wait. I hope you can see it's moving up. I don't know from your side how it's look, but here I don't know. Can you see the thing is moving up or
No, sir.
no? Because this is the problem using the webcam here, because what we call this. Okay, can you see? No, right? Because it's white and also white. That's why our eyes is pretty nice. This webcam, they have glass. This also glass, so the reflection, the whatever, so on. So that's a problem. No matter what. But the idea later on, I will show you in front here, what will happen. So basically now, like the one what we do with our water and tissue paper, the water goes up. But because there are glass here, so maybe the reflection from this also glass, so you cannot see very well lah. Because I'm using just a webcam, not a camera. So that's why I'm sorry for that. But at least now, I just tell you what happening now. It's moving up. No, it's not good lah if you cannot show this. How about I show like this? Wait, No, I need to wait first. Because now the water, not the water, the solvent rise up, we need to stop until it reach the top one. Okay. So I need to stop there, but so I cannot move first because I need to take, once it goes here, then we need to stop. You need to take out the thing. So later I will set the camera first. But now I need to wait because now it's near the what you call the top. After this, I will use the camera. Hopefully you can see lah. Okay, now. Okay, nearly. 2 seconds, 1 second. Okay, done. Oh, basically you need to close actually. Okay, that's better lah. So we take it out. Okay, so if you see under here, can you see here? I don't know whether you cannot see. I think it's already dry. So this is one of the problem using this thing. It's already dried lah, I think. But it's okay. We're done with this. Let me set the camera so that you can see better. Okay. Wait, I need to set the thing so that it's facing the. Wait for a minute. I don't know whether this will become better or not, but yeah, wait for me. Okay, I hope this will become better later on. Okay, so let me check whether you can see this. Let me change the scene to the, is it already on? On. Wait. Okay, so let me go here. Okay, so I will zoom that there. I hope it will become better later on. Let me put first. Let me put first the second, what we call second paper, TLC paper inside this. Okay, I put that carefully. Okay. So here, let me check. Can you see now?
Yes, sir.
Clear, more clear.
Yes, sir.
So that's why. Yes, okay. So that's what I saw. So I'm using the camcorder now. So yeah, wait. Yeah, I think you can see now the thing going up. So you need to stop. You need to pull it up. Wait, I need to adjust my camcorder. You need to pull it up once the solvent reach the top. So this is what we call why we call the solvent as a mobile phase, because it's mobile, it's moving, and then while it's moving, it's sort of like kicking the compound on the TLC plate. So they are doing the kicking now. Wait, remove this. Now it's difficult, but I want to try to get it better. No, near is not. You need to go far. So I think that's clear here. Yeah, just itulah. Okay, so now it's kicking. Okay, so now we wait until it goes until reaching the top. Okay. The idea. Okay. Question. Anyone can give the idea. What happening now? What happening now? What happened when the solvent goes up? What happening to the compound that we spot early on?
The compound move.
Move. Okay. Who's that? Azamuddin.
Yes, sir.
Azamuddin, are you the one
Yeah.
who WhatsApp me yesterday?
Yes.
Okay.
Yes, sir.
Okay. Okay, so it will kick the what you call the compound. Oh, by the way, about the bonus mark, I will check again this. So now it's on the top. So about the bonus mark, I will check again the name later on after finish ni lah. Because I record this thing, so that's okay. So later on, I will see which one, who are answering and so on. So now this is the last one, the last for the X. So we put there. Okay, again, and we close that. So now I think you can see. Let me check. You can see or not? Yeah, I think you can see it's moving up, right? Okay, so the idea is this. Okay, needs explanation lah while waiting for this. The idea is this: the compound can be polar and non-polar. The one that you spot can be polar and non-polar. Although we can dissolve it in dichromethane, although it's normally non-polar, but when we say polar and non-polar, it's not like 100% polar or 100% non-polar. It's more like a combination of polarity. So one compound maybe have polarity 90%, like that. So it's not like when you have a compound, it's totally polar, it's totally non-polar. So different polarity will attach to this silica gel, the white part, differently. Silica gel is polar. Okay, the silica gel here, the white thing here, is basically polar compound. Okay, so if you put a compound that is polar, if you spot, if let's say you spot the compound that is polar on the silica gel, so they sort of like, the silica gel will sort of like adhere, it will absorb strongly. So the silica gel sort of like hold that very dearly lah. Okay, because it's polar and polar, so it will hold them dearly. So if you try to kick with the mobile phase, the polar compound will move slower, will not move much lah, because the silica gels already sort of like hold them tight. So that's the idea. So if you have two compound, one is polar, one is non-polar, then the polar compound normally, in this case, the polar compound will be at the bottom, will be lower than the non-polar compound. So this already done. So I need to take first before I forgot. So we done with the X. So let me, this we dry first. We dry. Okay, now we done with the X. Remember, we have also Y. So we remove this, we put somewhere. And then we have another, this is for Y. This is for Y. And then we open, and then we put the Y. Let me take first. Okay, so this is Y, one of the Y compound that we did before. So we put inside, so because this, so this is easy to see lah here. We put here. Okay. Okay, so now continue just now. The polar compound will sort of like grip to the silica very tightly. So the polar compound, if let's say one of the compound here is polar and one of the compound here is non-polar, this solvent will push the non-polar up, okay, because the non-polar compound will sort of like have less stickiness to this plate. That's one of the idea lah. Okay, the reason why this solvent is different than this solvent, for example here, the one that we used before is DCM and also hexane 9,1, but this one is, I think, the hexane and ethanol, is because why? Because what? Anyone? Question? Anyone? This is question. Why you use the different solvent? You can answer this, you get 2 points.
Can I try?
Yes.
Maybe because the first solvent can be contaminated by the earlier compound.
By the compound, the first compound.
The earlier compound.
No.
The X one.
I mean, okay, you get one only lah. I mean is that this we use for the X. All this, the previous one that we use is for X. We use the same solvent, and then we put three plate, right? we not contaminate this solvent because remember our we have line here. So we put the solvent is below the line. So the compound is on the line. So that's why it will not contaminate. Okay, we take it first before I forget. So this is what? This is acetylene. So now we put the second one here. Okay. Okay, it's not because of contaminate or not, because by right it will not contaminate. Our compound is on the line, which is above the level of the solution. So contamination is not the reason. The question that I ask is that why, the unknown why, we use this one, but for the x here, we use another, what we call, y is here, the x is here. Why we use a different solvent? That's the main question. Why not use the same solvent?
So can I try?
Yes.
Is it because the different solubility for different compound?
That's correct also, but can you explain more? Can you explain more? Now you get 1 mark. You get another mark. You need to explain a little bit. Just anything. Just what is the logic behind that solubility and also different ni. Just explain in such a way that your friend can understand.
Sir, can I try?
Yeah. Okay. What's your name?
Mariam.
Mariam. Yeah. Why?
Because polar compound dissolving polar solvents and non-polar compound dissolving non-polar solvents.
Okay, but this thing, we don't say this is polar or non-polar. It's just they have some polarity here. There are some polarity here. Meaning that this solvent here is not totally polar, not totally non-polar, because we mix polar and non-polar. Same with this, we mix polar and non-polar. So the thing is, the answer is that, wait, we already finished this here. So we take it first. So the reason is that different mobile phase will kick at different rate, meaning that will travel at different rate, and also that can have what we call, can also sort of, let me put here first because I cannot talk while doing things. It's quite difficult to do that. Okay, the idea is that different solvent here, this and this, they have a little bit different polarity. So because of that, they have different behavior when it meet the silica gel. Okay, same like a compound, because if you have a polar compound, they will stick very tightly to the silica gel. Similar to this mobile phase, it's same like a compound also. Just this mobile phase can move. That's the difference. If you make this mobile phase is more polar or more non-polar, depending what you want, it will give rise. It will rise at different rate, and this is important because if you have something that is very polar, for example, if you have a compound X, let's say this compound X is very polar, it will grip on the silica gel very tightly. So you need something to push. You need something to push, something stronger to push this what we call this compound from the silica gel. So you need to use maybe a different what we call polar. You need to play around, and how you do that is that you play around with the polarity of your eluent or this mobile phase, because different eluent or different mobile phase have different capability to kick the compound. If the compound is very what we call very polar, you need something that is capable to push that so that you can see the separation. If you just use the same mobile phase for everything, then you cannot lah. You just stay there. It will not separate. So that's the idea. So now you can see it's already the end. So that's good. So we take it out. So that's basically TLC. Now, let me change the camera first. Let me change the camera here. What here? Okay. if you look here on here, this is what we call, let me make it smaller here. Wait. Okay, let me, okay, that's thing. Okay. If you see here, this is Y and this is X. Okay. You cannot see anything there. Even though you already do this, what we call the solvent, whatever, the TLC, but nothing is shown here because of, as I said before, organic compound is colorless, so you cannot, even though it's separate, but you cannot sort of like detect, you cannot see. How to see this? There's nothing there. That's why they bind with the gypsum that we discussed in the beginning. So for that, to see that, we let it dry for a while. Maybe this already dry. So we use our, what we call, our what? Question.
UV light.
Yeah, siapa tu? What's your name?
Mariam.
Mariam. Okay. So we use this UV light. Okay. So because this UV light, if I shine it like this, okay, basically I will use this 254 because that's what on the one that here stated here on this their ni 254. So I will use 254, and 254 being very energetic, it can be dangerous for you lah. So that's why I wearing the glass, the plastic. If you see in laminar flow, I show the picture in laminar flow. During when you do UV in laminar flow, you will close it with plastic. UV cannot penetrate plastic. It cannot penetrate plastic lah. So that's why when you are in the house, the UV light from the sun sort of like being blocked by glass. Glass can go through actually, but if you have plastic, then glass, I think glass.
Sir,
Yeah.
can I ask you a question?
Yes.
Why do we use UV when it is harmful? Why don't we use a staining agent?
Staining agent is you can, but then it will sort of like staining agent. You need to understand one thing. If you want to do staining agent, if you do staining, it's maybe less harmful, but of course staining also harmful. If you use like gram staining, you use Lugol, you use iodine, that's also harmful. The thing is that when you use staining, one thing is that it destructive. The test is destructive, meaning that after you stain, if let's say you want to use again that sample, then you cannot, because the stain will sort of like complex with your compound. So that's one thing. It's destructive in nature. UV is non-destructive, meaning that you just shine the light, and then after you close the UV, then you can peel the compound like that. So it's not destructive in the sense lah. So that's one thing, destructive or non-destructive. Secondly, staining, you need to sort of like you see on top of this there are 3 different things. Compound A plus something, compound B, whatever lah. So that if you want to stain, normally to be specific, you need to have a specific stain to specific thing. Okay, because stain work by binding with some molecule, whatever. So it need to bind with whatever the X, the whatever B and C. UV is different because UV we are just visualize what we are UVing the silica only. We are not cause any, we are, because here you cannot see because they are invisible to you, but it will be visible under UV. It's like night vision lah. If you have infrared, for example, now me, if you have a camera in front of me that is IR camera, you can see me glowing lah, because heat, whatever. So IR infrared camera can show you your heat, your temperature. So we cannot see now because you are seeing me using the normal light. Same like here. Here we cannot see, not because they are not there, it's because we are not capable to see it. If we use UV light sort of give you some fluorescence lah. So that's the idea. Staining is okay, it just you need to be very specific, and also for each compound you have a different staining agent lah. So that's the reason. it's not, it will not, you need to make very specific. You need to do like the X, one TLC only for X only, one TLC only for Y, one TLC only for Z, whatever like that. So it will take a lot of TLC, and at the end, the cost of staining will sort of like outcompensate the harmful of the UV, because UV, as I said, it can, you can block the UV using the plastic. For example, where is my plastic? Where's my plastic? Where is my plastic? Yeah, this plastic. If I put like this, if I put like this plastic, this plastic. If I put in front of me, then it will, it will sort of like block the UV. So now, if I open this thing, the UV, so I will open the shockwave. Okay, so you can see something. You see the green one, right? But it's not clear, right? Because I need to close the light first. So let me close the light, and then later on I will change to the camcorder view. So I will close the light first, switch off the light first. Wait. So we already at the end of our ni. So maybe another 10 minutes. We already done. Okay. Okay, so now I'm already switched off the light in this lab. So if I, and one more thing, I'm wearing the shirt now. So this also sort of like this shirt, this is lab coat. Lab coat or your shirt also can prevent the UV light. That's why if you go to the beach and you don't wear anything, then you get sunburn. The sunburn is caused by UV from the sunlight. So the shirt also sort of like can block the UV light. Even though UV is harmful, it's easy to block the UV. It's not like gamma ray or radiation, whatever, the very high radiation. It's just, you can block it easily. You can just block with just this what we call this glove and so on. So that's why when you want to work with the UV, wear glove lah. So let's say I open this long wave. So this is long wave. Okay, you actually, when I do long wave, nothing happen. Nothing happen. You don't see anything. Okay, this is long wave. Now I switch to the short wave. Okay, so you can see something, but I think it's difficult to see. You can see, right? I think,
Yes, sir.
Oh, you already can see. So I don't need to use what we call the camcorder lah. So you already see this thing. So now you can see this is X. So let me check. This is X. Oh, you cannot see because this is dark. But basically, yeah, you cannot see. This is X here, Y here. Okay, you can see now using UV, you can the TLC will be fluorescence. Okay, I think it's clear, right? It's clear. Is it clear? You can see the dot, right?
Yes, sir.
Okay.
Yes.
Yes, sir.
Last time I checked, it cannot. But it's okay, that's good. Maybe because it's darker now. Anyway, so now you have this. You can see this, but if I close the UV, then you don't see anything. Okay? So that's why you need to trace the thing, because now without UV, you still lost. You don't know which one is which. So that's why you need to have like a pencil around you. Where is pencil? Where is my pencil? Yeah, this pencil. I have pencil here. This is X, this is Y. And then we will trace the outline. Okay, so I open the UV, the short UV. Okay, takes time first. Okay, now. Okay. That. Hope you can see. Yeah, let me zoom first. Let me zoom. Zoom, you cannot see. You can see, yeah, you can see. Oh, let's do one by one lah. This put here, this one here. Much clearer lah. This is X. This is X. So now I will trace this thing using pencil. I'm using pencil. So I will trace this like that, this like that, and this here, and this here, and this one is here, and then this is here. This is what we call bleeding. It goes a little bit, go away here, it just mind its own business, but it's around here actually. Yeah. And this one is here, this one is here, and then this one is here. So now if I close this, then you can see the what we call the trace there, and this is useful for you to check what we call, you cannot see me, it's useful for you to check the RF later on. So let's do for the Y. Okay, this is for the X. So let's do for the Y. Okay, so that is Y. Okay, so now, what is this? So you have here, actually you have something here like this, something here, you have something here. Okay, it's good for you to, it's good if I wear the, what we call this thing. You see, I have this plastic I put in front of me. Okay, I put in front of me. Basically, this plastic I put in front of me to avoid this UV radiation lah. But that's why when you use UV, just use a little ni lah, just a short period lah, and wear glove. Here and here is like sort of like mixed together, meaning that it doesn't have, they are separating, but they don't have much time. Anyway, so this is here, and then this one is here, and then this one is here, and then this one is here. Okay, so we done that, and then we close the UV. We done with the UV. We open the light. Wait, I will open the light. Okay, so that is light on, and then we move this UV over there, and then we are zooming out. No need to zoom in lah, because you can see clearly here. Okay, so now you can see this is X, the X on the top, Y on the bottom. Okay, so now the question, based on this, what is X, and explain. You need to explain, not just say what. Explain. What is X, and explain why. You see here, this is X. This is X. Okay, this is X. So let's look at X first. From this thing, what is X? So you see, let's say in the middle here is, let's say I put it, let's say this is 3 nitro. This is 3 nitro. This is naphtha. So I make it bigger lah. What is the thing? So I make it bigger. I hope you can see now. Okay, I hope you can see the I don't know whether you can see or not. But which, let's say this is left, middle, and the right. So anyone, what is X?
Sarah.
Sarah, okay. What is X, and explain why based on this TLC result.
X is vanillin because the distance traveled by the X and distance traveled by the vanillin is same.
Yeah, so that's the idea lah. So what is Y? It's free mark. What is Y? Other person. What is Y?
Methyl.
What is your name? What is your name?
Mariam.
Mariam. Okay.
Yes.
What is Y?
The third one, methyl for natural acid.
Metal for something. Why?
Because as Sarah said, the distance is the same.
Yeah. So that's the answer lah. So that's how you do this TLC identification using TLC. If you look here, the Y here at the asenapylene here, because we combine in the middle here, it will separate into two. Here, we combine in the middle, it will separate also, although it just like not separate too much here, but it will separate also lah. But here, because Y and whatever here, methyl for whatever, is the same thing, so it doesn't separate. So that's the idea of TLC. And this also the same lah. For the X here, the middle here, we combine X with the 3 nitro, so it will separate. And here in the middle, we combine X with naphthalene. So where is the thing? So maybe it goes far lah. Where is the another thing? Let me open this thing. Let me open this. Okay, there's nothing. So, okay, this is a problem here. If you see like this, if you see like this, okay, I put on the thing. Okay, if you see like this, it's as if the X is naphthalene. Okay, as if X is naphthalene. But the correct answer is vanillin lah. Yeah, because you see the naphtha is here, but here there are no naphtha separation here. You know this, you combine X with naphtha, but where is the naphtha here? The thing is, okay, the question, why? Why there are no naphthalene around here? There are naphthalene here. Where is here? Why is missing? Anyone? Question? We are the end now. So anyone? Why there are no naphtha in the middle?
So this is no Sarah.
Sarah, okay, Sarah.
I think it's because the spot is too big for naphthalene, or either or.
Okay.
And because of that, the mixing is not correct.
Okay. The TLC is very, what we call, very sensitive. So even though you put very small or big, it doesn't really matter. The reason for this is maybe naphtha bleeding to the side. It goes to the side and so on. Because remember, when things happen, you don't know. Maybe the naphtha goes here, it goes somewhere here like that. Or go far from here. Maybe it goes up until you don't see it. So that's why the choose of the solvent as a mobile phase can make a difference. If you have, for example, if you do this thing, everything spot you see, you don't see any spot, maybe the spot is already here, already like going, out of this thing lah. Like our, what we call, like our this thing. Like our this, if you remember, this is our, what we call, the tissue paper and also the green color. So you see here, you can see the green color is already there. So meaning that it's too powerful. The water is too powerful to push this thing. So that's why we use different, what we call different, we try to mix here and there to find the correct, what we call the best, the optimum solvent, so that the spot is in between. Because only when the spot in between, you can calculate the RF. So that's the idea. You have a different solvent combination. And how to find that? That is like try and error. You need to find this plus this plus this plus this and so on. So this is, okay. So that's the reason for this. So this is what we call bleeding. Maybe naphtha goes that. And this is basically why the vanilla, what we call, is vanilla, because everything is the same place lah. So how to calculate the RF? This may be the last question. How to calculate the RF? Anyone?
Yes, Nisa.
Nisa, okay, Nisa. How to calculate the RF?
Total distance by substance divided by total distance by solvent.
Total distance from where to where? Total distance from where to where?
From the line P
Line until
the circle.
Until the total distance is until what? From here to
To up to the circle.
here.
Solvent front.
Here.
Yeah. No. Yes.
That is what? Total distance or what?
Total distance.
So RF is what?
Total distance by substance divided by the total distance by solvent.
Total distance by solvent is from where to where? From here to?
From here to up until the line.
Until the line.
The very, yes.
Because we are moving our solvent there. Okay. So now, last question. Last question. In terms of RF, when RF is lower, when RF is less, what does it mean? Let's say you have RF 0.2 and RF 0.8. RF 0.2, if you compare this thing, which one is RF 0.2? Which one is RF 0.8? 0.8 roughly.
The one that has
Your name.
Mariam, sir.
Mariam. Okay, which one is RF 0.2?
The one that moved lesser has a smaller RF
Okay.
compared to the one that moved more, like higher.
Okay, so this will get lower RF and this got higher RF. So that's how to find the RF. So if you, let's say you have RF 0.2 and then you find another thing 0.2 also, then you can say it's the same thing. So that's the idea of TLC. So I just show this first. So later on, you can check this RF by taking the picture and so on. So this is basically the X. So this is 3-nitro whatever. This M-nitro, what is the thing? So this is M-nitro acetophen. This is naphthalene, and this is vanilla. There are X here, there are X here, there are X here. Okay, so next, this is Y. Okay, this is Y. This is the image for Y. Okay, so this is Y. This is Y plus S-naphthalene, and this is S-naphthalene. This is Y. This is Y. This is Y plus benzyl, and this is benzyl. This is Y. This is Y plus methyl 4-nitrobenzoate, and this is methyl 4-metrobenzoate. So I think that's it for today live stream. So any question for that? Any question? So that's the end of our live stream. Any question regarding the TLC? Hopefully by now you can understand what is TLC is all this 11. Yeah. Any question? Anyone?
No, sir.
No, sir.
No? Okay, so we end our live stream today with a recitation of Tasbih Kal-Farah and Suratul As.